Hello, everybody. My name is Konstantinos Hitsios, and this is a video walkthrough of our poster for the paper Automated Generation of Issue Reproducing Tests by Combining LLMs and Search-Based Testing, on behalf of myself, Marco Castelluccio, and Alberto Bachelli. So let us start with the problem we're trying to tackle here. Let me zoom in first a bit, so it's a little bit more visible. Super. So suppose you're a developer and you're working on a repo. And what usually happens is that users submit issue reports in that repo. For example, this issue report says that calling the max function without argument raises value error, but it should return -infinity instead. And what happens then as a developer, you usually come up with a patch, you or an LLM, maybe these days, come up with a patch that resolves the issue. In this case, this patch removes the value error, and now the code successfully returns -infinity. And the question is, are you done now that you have the patch? The answer is not exactly, because there's still one question that remains. This question is, what if this issue is already reduced in the future? How can you prevent this? The answer is through testing, of course, but not any testing. For example, let's have a look at the first test here, test max1. It asserts that the maximum value of 1 and 2 is 2. This is obviously correct on the one hand, but irrelevant on the other hand, because this assertion is true before the patch. It's also true after the patch, so it does not really help. If you have a look at test max2, on the other hand, it asserts that the maximum function without arguments equals to -infinity. And this assertion would fail before the patch, because this would be a value error, but it would pass after the patch. So this is what we call a fail to pass test, that we also denote like this. So the problem is that developers often omit these tests. So this opens up a nice avenue for automation, and our tool tries to automate this very task with you take as input an issue in the patch, and the output is a fail to pass test. So this, by zooming in here in our tool, you can see again the inputs, the issue description, and the patch, and the outputs are a fail to pass test, or maybe even 2 fail to pass tests. There are 2 components in our tool, an LLM component and a search-based software testing component here in blue. Let me start with the SBST component. What you want to do with SBST tools in general, they take as input a file or a module, and they generate passing tests for that module. So our idea here goes like this. I have the patch. From the patch, let me extract the files that were modified. And for these files, I will ask SBST tool, in this case Penguin, because it is on Python. Penguin is the state-of-the-art SBST tool on Python. Let me ask Penguin to generate a passing tests for the patched version of the file. Why passing tests on the patched version? Because we want a fail to pass test. So we already have the P here. And then let me run these tests in the body code. If any of them fails in the body code, then we have a fail to pass test by definition, right? It fails in the body code, it passes on the patched code. But the limitation, if you do it like this, is that the SBST tool cannot encode the natural language information of the issue you see here. So what we do is we add a seeding mechanism in the beginning. What this seeding mechanism does is it feeds the issue description and the patch through an LLM in the beginning. And we ask the LLM to generate a raw seed. A raw seed is a test in the format that is acceptable by Penguin. And Penguin has limitations, as like any other SBST tool. It cannot work with arbitrary tests, for example, tests that use introspection, that dynamically create classes. This cannot be handled by SBST because it's based on static and dynamic analysis. So we ask the LLM to generate a starting seed with many restrictions to adhere to Penguin standards, and we even further deserialize it through our own static analysis script to remove any statements from the test that do not comply with Penguin's representations. So what you end up with is a seed that encodes natural language information like functions or magic values or stuff like that. And then you start the penguin mutations from there. And then you again end up with a failed to pass test. And we'll find that this seeding mechanism indeed helps in our ablation study. Now let's go back to the LLM component, which is the second component of BLAST. And the main idea here is that okay, let me ask an LLM, let me prompt an LLM to generate a failed pass test. I mean, LLMs are state of the art in many test generation tasks. What do you feed to the LLM then? You feed the issue description, of course, here, but then you're missing a lot of stuff. So you also need to add some information from the patch. What you do is, again, we extract the modified files, and ideally, for example, in this case, we would like the LLM to see the min-max base class as well, because this could help in the test generation. But this class is, of course, part of a bigger file that could be thousands lines long. So what you do here is you filter only the focal context, and the focal context is exactly this. If this is the patch here, the focal context is the class, the direct class in which the patch changed. So we extract it here and we pass it to the LLM. And then we make another observation that you want to generate a test for this class, right? Wouldn't it help if the LLM had access to other tests for this class? And this is what we do here. We want to find the most coupled test file for this class. And there are many ways to do it. One straightforward way would be to run all the tests and see which test covers this class the most, but this would be, of course, very expensive to run all the tests. So we come up with a static way of doing this, and it's called temporal coupling. It has also been used in literature, in the mining software repositories literature, and what it says in simple words is, okay, I want the test that is more relevant to this class. Let me go back to the Git history, and for every commit, and detect every commit that changes this class. Now I have n commits. Let me find out which test is changed in these n commits the most. This would mean that whenever you change this class, you also change that test file. And this is what we do. And this is how we derive the most coupled test file. Again, for more details, you are invited to have a look in our paper. And now we have all the context we need for the LLM. Or do we? Because then we also thought about something, an additional source of context. We already have generated some passing tests here with Penguin, right? We already have done this for the SBST component. So we say it wouldn't harm if we include these passing tests to the LLM, because these tests have two nice properties. They pass in the patched code, and they are syntactically correct. By definition, Penguin generates syntactically correct tests. And this is what we do here in number 5. We also include these passing tests in the LLM as a prompt, and then the LLM generates a raw test function. We inject it back to the test file we found here to be most relevant. Then we run the test, the generated test in the backend, the fixed code, and hopefully we get another failed pass test. This is what we also describe here. This is our tool BLAST. And now let me walk through our 3 research questions. In the first research question, we compare BLAST to LLM-only baselines. We use a curated version of SWT bench. And I say curated because we discarded 23 instances where the issue description itself contained a failed to pass test. So the task was trivial there. We compare against the zero shot, is a simple zero shot LLM query, and O2TDD, which uses a 3-step LLM pipeline to gather relevant context and generate the test. And as we see, using 3 models, GPT-4o, Llama 3.3, and DeepSeek, BLAST outperforms these baselines. Then we go on and do an ablation study to see, because this figure you see here, it has many things, 1, 2, 3, up to 9. And what we do here, we turn some things off and then we measure the impact. This is what we do for our second research question, and we find many things. The details are in the paper, but for here in the summary would be something like that the SBST component contributes a percentage of 7.3 failed pass tests that were completely missed by the LLM component. And this is a nice increase, but the percentage may seem a bit small in the beginning. But if you think about it, it's not that small for two reasons. First, this 7.3% is on a subset of all the SWT bench instances, because as we mentioned also earlier, SBST tools cannot run on arbitrary code. So out of 400 something issues that SWT bench has, Penguin successfully runs without error in 113 issues. So this is 11 out of 113, not 11 out of 400. And this means that if future versions of SBST tools support more arbitrary code, this percentage would automatically increase. And another thing that we found could be fixed by future work is we analyzed 20 non-fail to pass tests generated by SBST here. Only 10 of them even covered the patched code. So even 10 of them even reached the patched code. And this is because the SBST right now takes very coarse-grained inputs. So the only thing you can say to an SBST tool is generate passing tests for this module, so for this whole file. If in the future there are versions that support more fine-grained targets, that you can say, please generate tests for this function or even these lines, then this percentage would also automatically increase. And now let us move on to our third research question, which stems from the fact that the first two evaluations, they are done on historical data. So SWT bench contains issues that go back to 2013. And this can have two limitations. First, you don't know whether the LLM has seen some of these issues, has memorized them. And secondly, does not take into account the developer's perception. So what we do is we conduct the first in vivo evaluation of an issue reproducing test generator. We do this by deploying BLAST in the 3 Mozilla repositories that you see over here. And we deploy it in a way that we implement the GitHub bot. The GitHub bot listens for new PRs. If a new PR comes in this repo, and this PR is linked to an issue, then the bot extracts the issue description, the patch, and it runs BLAST. And if a fail to pass test is generated, it is proposed to the developers as a comment to that PR. Now, BLAST was run 32 PRs. The best LLM, which is Llama, performed generated 8 fail to pass tests, but in total, using also GPT-4o and DeepSeek, we proposed 11 fail to pass tests to developers. Now, out of these 11, 6 were considered to reproduce the issue by the developers. And some comments were like, valid test, I'm adding it, and indeed some tests were added in the test suite of developers. So that's certainly good. But this is what we also found, that would not be possible to find through automated evaluations, that 5 of the fail to pass tests were not useful at all to the developers. And this means that treating fail to pass tests as de facto useful is not a valid assumption. So some manual analysis or some developer validation is needed. For example, here is a comment that we got for this, that the test would be perfect if this was a regression. But this is a future, so a regression test would not be much relevant here. One thing you could do is to have the bot act only when the PR is linked to an issue with the type bug. And this is what we did. Finally, we changed the bot to only act on these PRs. But an important observation here is that benchmarks like SWT bench, they don't do that filtering. So they consider PRs that are bugs, are new features, or whatever. They don't do any filtering. And this is a nice antithesis. And here's also an example of a fail to pass test that is not a useful issue reproducing test at all. You see that the patch added a function to handle missing comments. And this is a fail to pass test, right? If you run this test, it passes in the patched code and fails in the byte code. But if you look closely, what this test does is just calls this function with the default arguments and asserts a default functionality of this function. This could fail in the unpatched code because this function does not even exist. So the failure is trivial. It's not really a failure. And of course, it would pass in the patched code because it asserts a default behavior. So yes, fail to pass, yes, but useful not. So this is it. Thank you very much for attending, and looking forward to seeing you in Seoul.